Okay, so in this set of notes, one, we are finishing chapter 3 of differentiation, and 2, we are going into something called related rates. So this is kind of a culmination of all that we've learned in chapter 3 here. So what is a related rate? Well, it's a problem that you want to solve an unknown rate for that is written in terms of other rates that we know. When we do these problems, we want to kind of piece together all the information that we have, give them labels, write down what we know and what we want to know. So I'm going to go through example 1 and kind of start showing you how to start this process. So number 1 is filling a conical tank. It's important that you know that a conical tank looks like an ice cream cone. So water pours into a conical tank at a height of 10 meters and a radius of 4 meters at a rate of 6 meters cubed per minute. At what rate is the water level rising when the level is 5 meters high? I'm going to draw a visual of this. And it's really important that you only put things in your visual that are staying constant or staying consistent. So the height of the tank will always be 10 meters. The radius of the tank, at least at the tip of the cone, will always be 4 meters. The rate that the water's going in, always 6 meters cubed per minute. The thing that's changing is that the water level is not always 5 meters high. When it first starts going in, the water level is 0. At the end, the water level is going to be capping off at 5 or 10 meters. It's not going to be any higher than that, otherwise it's going to overflow. So I'm only going to be drawing a cone with a height of 10 meters and a radius of 4 meters. Now I can go ahead and draw in the 5 meters for later on, but I'm just going to label it H for height. At some unknown time later, and then the radius for that R for some unknown radius later. Do you have to put those in there? No, it's just an option. So then I'm going to start labeling some other pieces of information, like our rates. I see a rate of 6 meters cubed per minute. I know that that's the change of my volume because I see meters cubed. And because it's per minute, I know that my independent variable is time. So this I would call dV for the change in my volume over dt for the change in my time. And I want to know the rate the water level is rising. So rising being height, telling me I want to know the change in the height over time. I'm going to make that look a little prettier. Here we go. And I specifically want to know the change in the water level's height over time at 5 meters high, or when the water level is 5 meters high. All right, so I know what I want. I have what I'm given, but I'm going to write that down specifically. And that's about it. I'm not going to put that the overall height is 10 because I have that in my visual. I'm not going to put that the overall radius is 4 because I have that in my visual. So trying to think about how I can put this information together. I have volume, I have height, I have radius. I think it would make sense to first and foremost write down that I need a volume equation. The volume equation will get me my volume, radius, and height. And if you don't know the volume of a cone, I don't know that off the top of my head every year. I have to go look it up. That's fine. But I can tell you now, it's 1/3 pi r squared h. Now, the reason I have equations and then with an S in parentheses is because you will sometimes need secondary equations. If I look at this and I go to take the derivative with respect to time, I'm going to end up needing to use product rule on the right side and doing implicit differentiation. I'm going to end up with 3 different rates: dv dt, dr dt, and dh dt. I want to know dv dt. I know dh dt. That means that I also wouldn't know dr dt. You do not want to have more than one unknown variable or one unknown rate at a time. In fact, it could be okay if we have more than one unknown variable if we have more information that we could use to solve. But you absolutely do not want more than one unknown rate. Write that down. Do not want more than one unknown rate. If you do, you'll need a secondary equation. I'll have that pop up here. There we go. So you probably don't know what kind of equation you can come up with from here. But if you look at our diagram, we do have proportions that we could write up. We have a radius height proportion and a radius height proportion. And you will end up seeing similar things in subsequent problems. Like if you have similar triangles drawn within each other, you can go ahead and write proportions for that too. So it's kind of like I have a mini cone drawn within my overall cone. So I can go ahead and write a general equation for radius over height at any given time equal to my overall radius and height at the end. And that gets me an equation where I can get rid of my r variable in my volume equation, so I don't have to have the derivative of r when I go to take the derivative here. So I'm going to go ahead and solve my secondary equation for r and replace that in my volume equation so it disappears and I don't have to deal with it. Let me know what you get when you solve for r. All right, I'm getting 0.4 h, or you can say 4/10, or you can say 2/5 h. All of those work. Now we are going to take that and we are going to plug that into our volume formula, which I'm going to write down here. In fact, there's really no point in me circling this, but I guess we'll leave it. All right, go ahead and simplify that. And we get, let's see, do pi over 3. 0.4 squared is going to be 0.8. I guess I'll leave this as 2/5 instead of 0.4. Yeah, I'll do that. That way I can make that 4/25. And then our final expression will be 4 pi over 75 h cubed. Okay, so now we have an equation of volume that is dependent only on h, and we will only have one unknown rate, the volume rate. We know our height rate. So once we have a nice equation where there's only one unknown rate, we can go ahead and compute the derivative with respect to, in this case, it's time. If it's per minute, that tells me my variable that I'm taking the derivative with respect to. And write that down. We are going to compute the derivative with respect to time. Now you might be asking me, but Ms. Sandor, I don't see any t's. That's fine. You're going to take the derivative of every variable like you normally would, but because none of them are t's, you'll multiply by d variable dt. Or you can use your prime notation, that's fine. All right, so our volume equation is V equals, here, I'll make it a little darker. V equals 4 pi over 75 h cubed. Okay. Derivative of V is 1, but it's not time, so I'm going to multiply by dv dt. I'm going to get rid of the 1. I don't like writing it. Equals derivative of 4 pi over 75 h cubed. Use power rule, multiply by the 3. And if you do that, you get 12 pi over 75 h squared, but that's not a t, so I'm going to multiply by dh dt. And now I can go ahead and plug the information that I know in. I wanted to know the rate of my height, or the rate that the water level is rising over time when my volume is changing at 6 meters cubed per minute and when the height was 5. So I'm going to plug that information in. Okay. I'm going to go ahead and plug this expression into my calculator, get that rounded out to a few decimal places. All right, I'm going to take that to 12.5663 or 12.5664. Divide that to the other side, and we get that the change in height with respect to time when the height is 5 is 0.4775. What would the label for height be? Meters per, what's the label for time? Minute. And that is the answer that we were looking for here. If you have questions, make sure you write them down. And we are going to go to the next problem. All right, example 2. At a given moment, a plane passes directly above a radar station at an altitude of 6 kilometers. Go ahead and draw the plane station. Draw the radar station. Go ahead and draw the plane when it's directly above, and then maybe a little while later to show the movement. That'll be my radar station. I'm going to draw the plane here. I know it kind of looks like a fish, but I'll put like a wing on it, window, window, that's fine. Pretend it looks like a good plane. And then a little while later. All right, and then remember, we can put things down that are staying consistent. That plane, it's flying at an altitude of 6 kilometers. It's always going to be 6 kilometers above wherever the radar station was. So I know the absolute height this way is going to be 6 kilometers. Now, it looks like if I connect the distance between the plane later on in the radar station, like I have a right triangle. So I'm gonna guess that my equation will probably want to use something with what? What kind of equation do we use when we have sides of a right triangle? Pythagorean theorem, so keep that in mind. Now, just for consistency, let's all use the same variables to represent the sides here. So I'm gonna put maybe P for the plane distance, and then maybe R for the distance between the radar station and the plane. So let's see. I'm going to keep reading the problem, and then based on the stuff that we have labeled here, we can label our rates and any other information. So the plane speed is 800 kilometers per hour. So kilometers per hour. Hour tells me that my independent variable is going to be time. So would that be dp dt or dr dt? That's only the plane speed, so that should be dp dt. This is something that we know. What we want to know is how fast is the distance between the plane and the radar station changing half a minute later. How fast is the distance between the plane and the station? So we want dr dt. So I'm going to write my want and my know statements up. And specifically, we want to know that rate half a minute later. Keep in mind, how's our time measured? If you look at the rate that we are given. Time is measured in hours. And we are asked about time or about a rate half a minute later. So I am going to just automatically right now at the very top of my page, convert half a minute into hours. I know that sounds crazy, but let's do it. Go ahead and do that conversion from half a minute to hours and let me know what you got. That looks pretty gross, and that's not something I want around, so I'm going to leave that in fraction form. 1/120. Okay, so we want to know the rate that the distance between the plane and the station is changing at time 1/120th hours. Sounds a little crazy, but we'll go with it. And we know that the plane's speed is 800 kilometers per hour. So if you ever see that your labels, whether it's the label for your distances or labels for your times are different, you will need to do some sort of conversion. Make sure that they are all the same. All right, so let's get an equation together relating our variables. We talked about the Pythagorean theorem already. So here, a squared plus b squared equals c squared. C squared would be, in this case, p squared plus 6 squared equals r squared. 6 is allowed to be in there because it will always be 6 kilometers above that radar station. That is not changing. That's perfectly fine. And don't just leave it as 6 squared. Clean it up. Make that a plus 36. And the reason why I say to do that is because if you leave it as 6 squared, when you go to take the derivative, I can guarantee half of you will treat that as a variable and do 2 times 6. No, it's a constant. What is the derivative of a constant when we get there? 0, not 12. So actually write that as 36. Now, if we were to take the derivative with respect to time, we would have dp dt somewhere in there and dr dt somewhere in there. We know dp dt, we want dr dt. We only have one unknown rate then. We're perfectly fine. We do not need a secondary equation. We are good to go ahead and go straight into computing the derivative with respect to time. All right, go ahead and take the derivative with respect to time. We'll see what you get. Derivative of p squared is 2p. But because that is not t for time, I'm going to multiply by dp dt. Or you can multiply by p prime. I think I'll do that this time. Derivative of 36 is 0. And the derivative of r squared, 2r. But again, it's not a t, so I'm going to multiply by r prime, or dr dt. And we know that dp dt, or p prime, equals 800. But honestly, if we only plug that in, we'd still have quite a few unknowns. We wouldn't know p, and we don't know r at that specific time. But we can figure it out. We still need, and we're going to do a little side work. We can bubble this off if you want. We need to know p, and we need to know r half a minute later. Oh, I guess I'll say at. So we can actually go ahead and figure that out. We know the rate that the plane is traveling. We know that it's traveling at 800 kilometers per hour. So if we kind of treat this as position 0, we can use the rate that it's traveling to figure out where it is half a minute later, or 1/120th hours later. So for p, starting at 0 plus the rate of 800 kilometers per hour times 1/120th hours gets me, it's figured out, 6.667. That's fine, we can round that. That many kilometers later on. The reason I did start with 0 is because there will be some problems that the starting spot won't be 0. So you'll want to kind of keep in mind how to figure out later distances or later amounts. Then for r, what do you think we could do to figure out what r is, knowing that P for where we want is, and I'll erase this, 6.667 kilometers. Maybe what that R is. Hopefully you said Pythagorean theorem. All right, go ahead and solve this equation for R squared. I'm going to have my answer appear in 3, 2, 1. Okay, take a quick look through the work. Now we can go ahead and evaluate our derivative. And I guess I'll draw a little arrow down here. Oops. All right, so it was 2p times p prime. I'm going to ignore the plus 0 equals 2r times r prime, which we did not know. I'm going to go ahead and divide these two factors to the other side. Put that in our calculator and I'll put the answer up in just a moment. There we go, 5.94.671. And the label would be kilometers per hour. Example 2, part B. How fast is the distance between the plane and the station changing when the plane passes directly above the station? So in this case, we are wanting which rate? We want dr dt. And I'm actually going to draw the visual from the last problem. So if you want to go ahead and pause the video, I'm going to have my visual pop up in 3, 2, 1. So from part A, we have the derivative 2p p prime equals 2r r prime. And we also have our Pythagorean theorem formula. We want to know what the rate is when the plane is directly above the station. So basically, when our plane is directly above the station, what information do we know? That tells us that P would be 0. In fact, let me write that down. If you just want to write, we know, that's perfectly fine. And that tells us that R would actually be the same as our height. But you could always plug that into the Pythagorean theorem and see that R would be 6. I'm not going to, it's kind of redundant to do that. So in this case, we have enough information to solve for dr dt, or r prime. Plug in the information and let me know what you get for r prime. Label would be kilometers per hour. All right, moving on to part C, the very last problem in the notes. Let theta be the angle that the line through the radar station and the plane makes at time t. Now, just quickly, we are doing a completely different variable here. So we are going to be starting this problem from scratch. We cannot use things from the previous parts, except for, the fact that the plane started off 6 meters above the radar station. So we can still use that. So let me at least bring in the visual from earlier, but we probably will not be using all of the variables. Okay. So I'm just gonna read this from the get-go. If you needed to pause the video to put your visual in there, go for it. It says, let theta be the angle that the line through the radar station and the plane make at time t. So where would we place theta? Would it be here, here, or here? Hopefully you said at C. The angle that the radar station and the plane are making at any given time. So this is the plane at any given time. Okay. How fast is theta changing? So we want the rate that theta is changing. We want d theta dt at 12 minutes after the plane passes over the radar station. So remember, we're working with hours, kilometers per hour. We're going to convert that 12 minutes into hours. So we can use some of the given information from previous parts, but we are not necessarily going to need all of it. Go ahead and convert that. (12/60). 0.2 is a good number. If it was repeating, I would leave it in fraction form. And let's write down what we know. We know dp dt is still 800. That's the rate that it's traveling this entire time. The rate from the distance between the radar station and the plane, dr dt, that was changing at different rates. The only rate that's staying consistent all the time is the plane's speed. So that dp dt is always going to be 800 kilometers per hour. And we know that the height is always 6. So I don't even need to write that down. That's in my visual. There's nothing else that is staying consistent. So that's really the only thing that we can write down is what we know. Now, considering that I want to know d theta dt, I need to write an equation that involves theta. What are the only types of equations that you can use that are going to involve theta and a right triangle? Hopefully you said a trig equation. Now we have P that we know the rate for. We want to know the rate for theta. I don't need to have R in my equation at all. In fact, if I involve R, then I have two different rates that I don't know. So I'm going to try to write a trig equation that doesn't involve R at all. That way I can limit the number of variables that I don't know the rates for. So try to write a trig equation that involves 6 and P and theta. Let's see. The sides that I know in relationship to theta would be my opposite side for P and my adjacent side for 6. So I think it would make sense to write a tangent equation. Or you can do cotangent, whatever your heart desires. Opposite over adjacent. Or you could write that as 1/6 P. So thinking about this, I know the rate for theta, I want to know the rate for theta. I know the rate for P. Those are the only variables I have here. We're good. I only have one unknown rate. We are all set to go ahead and take the derivative with respect to time. So go ahead and do that for me. Derivative of tangent is secant squared. But theta is not t, so we're going to multiply by d theta dt, or theta prime. I'm going to use d theta dt this time. Derivative of 1/6 p, there's a reason I rewrote it that way. A lot of you, if you kept it as p over 6, we're probably going to do the quotient rule. Keep in mind, 1/6 is just a coefficient. So the derivative of 1/6 p is just 1/6. But p is not time, so we're going to multiply by dp dt. And let's see what information we have that we can plug in now that our derivative is done. We know dp dt is 800. We don't know theta, so we'll have to find our missing information. Now, you can either solve for theta, which I think is more cumbersome, or you can solve for secant theta, which is just the ratio of the sides from the triangle, and plug information in. So let's see. Secant is which side ratios? So reciprocal of cosine, so cosine being adjacent over hypotenuse, secant would be hypotenuse over adjacent. But really, I only know the one side of the triangle right now. So we have to figure out 12 minutes later what the plane's position would be. Started at position 0 plus 800 kilometers per hour times 0.2 hours. $160 kilometers. Now we still are going to need the hypotenuse, so we can use the Pythagorean theorem to solve for r. P squared is 160 squared plus 36 equals r squared. 160 squared plus 36. 25636. Square root that. And we get we'll round that to 160.112. All right, so that means that secant theta, if I go to draw this information into a right triangle, see 160, 160.112, and then this was 6. Obviously not to scale. Secant theta is hypotenuse over adjacent. So that would be, considering our right angle is here, 160.112 over 6. All right, let's go ahead and solve for d theta dt. I'll draw an arrow down here, plugging the rest of our information in. We had secant theta squared, so instead I'll put 160.112 over 6 squared times d theta dt equals 1/6 p prime. P prime being 800. Go ahead and finish solving for d theta dt, and the answer will pop up in just a moment. So it looks like we are getting 0.187 radians per hour. Moving on to just a general overview of the process for solving related rates problems. The first and second things that we want to do are draw a picture. In fact, I would kind of lump those together. Draw a picture and assign variables, rewrite the question using your want, no statements. Then you need to write an equation or equations that relate the variables, and then you can differentiate. But keep in mind, when you think about differentiating, if you are going to have more than one unknown rate, you need a secondary equation, which is what I had you write on the first page. If you'd rather write that here, pause the video, write that down. Then when you are filling in numbers, you don't want to substitute in values for the variables until after you've computed all the derivatives, unless that value is staying consistent. If you have a height that is always going to be 6 or something like that, you can put that in. But if that value changes depending on the time or depending on a different situation, you don't put a number in until after you differentiate. You want to keep a variable there for now. Then, given any information that you have, you can plug that into your derivative and solve for the rate that you want. You might need to solve for some additional missing information using maybe the formulas that you have or using some rates that you have, like we did in example 2. And some useful formulas. We know our Pythagorean theorem. And then we also have proportions. We did one set of proportions today for the conical vat. We knew the overall height. I'm going to try that one more time. Okay, good enough. We knew the overall height. We'll just call it, well, yeah, I guess we'll call that overall height. And then if we know like an overall radius, maybe we also know the radius at a certain time. So maybe a radius at time 1 and the height at time 1. We can make a proportion with that, putting the radiuses or the radii in one fraction, the height in another fraction, or if you want to do radius 1 over height 1, set that equal to overall radius over overall height. Doesn't matter so long as you're staying consistent with the placement of your values. Or maybe we have similar triangles. So if you have a triangle within another triangle, well, let's say maybe the overall triangle has length X here, Y here, and then I have another triangle within it, which would be considered a similar triangle, and that's length A and that's length B. I could write a proportion of Y over X equals A over B. Or I could do Y over A equals X over B. You could actually have better values than that with more specific information, but let's just pretend that's the information that we have for now. So that's what I meant by writing proportions. That is it for this video. I know it's been a long one, but we are at the end of chapter 3 now.